Hey everyone, Morgan here. So we are moving on to page 7 of the bonding outline, and we're going to talk about dipole moments today. Now, according to my physics textbook, a dipole is a separation of charge. Now, the only way that can happen is if you have two different charges, hence we call it dipole. Now, the greatest example, of course, would be magnets. Magnets have a permanent dipole moment. And if I take two magnets and I bring them together with opposite charges, they attract each other. However, if I turn that over now and I bring this magnet in and I'm putting the same charges side by side, what happens is that they repel each other, okay? And perhaps you remember this little demo from earlier in the year, where what I do is I put these magnets on this post with opposite charges. Sometimes I have to flip it around to make sure. Yep. And you see here that they have separated from each other. I push them together, I let go, it goes back, it does the same thing again. Now, molecules can have dipole moments based upon the type of bonding and their molecular shape. So we must remember a polar covalent bond. It is unequal sharing of electrons. Okay, so a molecule with a dipole moment is an unequal distribution of charges in a molecule. Now, we have to look at several different examples here to understand it. The first of which is going to be the H2 molecule, which has a Lewis structure that looks like that. It is a perfectly symmetric diatomic molecule. I can't tell the difference when I turn it around or anything like that. So what I'm going to say is that since both hydrogens have the same electronegativity, this is a non-polar bond. And because there's no lone pairs, everything's evenly distributed, I'm going to say it is a non-polar molecule. Which translates as no dipole moment. Now, what if I look at something like HCl, okay, where the atoms are not the same? So I've got my hydrogen, I've got my chlorine, and chlorine has a higher electronegativity. So the electrons are, in a sense, pulled towards the chlorine, or at least the electron density. So I'm going to draw an arrow towards where the electron density is. That would be the negative side. Here I'll put kind of a positive sign on the end of that vector so you can see it. Now, back a long time ago, what we used to do, and this is still common in biology books, but not with chemists anymore, is we put this symbol, delta negative, delta positive. Okay? Now, this is a polar bond. Polar covalent bond. Also, the molecule, since it is asymmetric, I can tell the difference when I spin it around, we're going to say that that is a polar molecule, or one that has a dipole moment. Okay. Now, boron trichloride. These chlorines are pretty electronegative compared to the boron, so the electron density is going to be close to them. And what happens is the electron density is basically pulled up that way, over that way, and over that way. And this is a trigonal planar molecule. It is perfectly flat. And each of these individual little pools will cancel each other out. So we say it has polar covalent bonds, but no dipole moment. It has 3 dipoles, but they cancel each other, hence no dipole moment for the molecule itself. Now, ammonia, NH3, the nitrogen's more electronegative, and it has a lone pair. Now, that looks more like this. And it's important to notice that it's not a symmetric molecule. If I turn it around, you can see the difference right away. Okay? So because of that, we do know polar covalent bond. That's the difference in electronegativities. And dipole moment. Or we also said it as that it is a polar molecule. Now this is going to be one of the single most important things we can really take out of this class to transfer over to biology and into physiology. Really important. Okay, so that's it for this page. Thanks for tuning in. This is Morgan signing off.